will be given by Rosa Michaela Danisi on Perettiite, yttrium, a new mineral from Monaik, Myanmar.
So, good morning, everybody. I'm very happy to be here and talk about the highlights in the discovery of Perettiite yttrium. Without any doubt, the identification of a new mineral represents an exciting challenge for a scientist, and I hope that you also share my opinion. And in case of Perettiite, this challenge was originated by Adolf Peretti. He identified yellow needles enclosed in idiomorphic phenakite crystals that he bought from a gem market in Mogok. Preliminary chemical analysis showed a very exotic composition with yttrium, calcium, manganese, and silicon. And this exotic yttrium-rich composition triggered our interest, and therefore we were motivated to continue with further investigations. But first of all, where are they coming from, these phenakite crystals with such exotic inclusions? Well, to answer to this question, Peretti initiated a field trip to Mogok in Myanmar. And probably you are already familiar with the Mogok and in particular with the Mogok metamorphic belt, because from here they are coming the world's finest rubies. The Mogok metamorphic belt consists in high-grade metamorphic rocks that are intruded by granitoids and pegmatites. And as you can see now in the picture above, pegmatites intruding peridotitic bodies in the area of Molo, north of Momeik, 45 kilometers from Mogok, are the source of these phenakite crystals with these yellow needles. Now we can see a picture of one of these samples, and you can recognize the peretite-bearing phenakites that form these prismatic crystals, mostly twinned, and they occur in a typical pegmatitic association with, of course, quartz, feldspars, and tourmalines. These few samples and geological informations were recovered from a local geologist that worked in the area of Mogok in 2007, because now there is the civil war there, so it's impossible to gain access to the Molo area. But now let's try to answer to the second question. So what are these yellow needles? And to answer to this question, we of course perform single crystal X-ray diffraction. So we had a very few material, so I could mount a crystal of around 200 micrometers on a glass needle. And what we obtained, it's such a diffraction pattern that clearly tells us that these crystals have a tetragonal symmetry. Please note that even at height 2 theta, there is no splitting of the reflection, indicating that, there is only one option, that the crystal is tetragonal. So what we did is to try to solve the crystal structure in tetragonal, using the tetragonal space group. But all the results that we got were physically meaningless. So in cases like that, so the solution could be that the crystal, of course, is twinned. So we have to lower the symmetry. And now we look at a crystal cross-section. This is a cross-section of 010. And what we notice is that the crystals are mimicking tetragonal symmetry. But under cross polarizers, they show this hourglass pattern with undulatory extinction. And that is suggesting us that so there is a problem with twinning, so the crystals are intimately twinned. And therefore, we interpreted this as a 90 degrees rotational twinning along the short axis. And so, therefore, we could solve the structure as a 50-50 pseudo-meroidal orthorhombic twin. There are other cases known in literature of this pseudo-tetragonal symmetry, and I listed all the cases known, and there we have semenovite, cerium, bismuthiite, and bayerite, and kettnerite. So now, let's have a look at the structure of perettiite. Our structure refinement allow us to describe perettiite as a borosilicate. So in the picture, you can see the borosilicate layer. And so we have in green the boron tetrahedra that are on a minor degree substituted by beryllium. And then we have in yellow the silicon tetrahedra. They are made up to form 4, 5, and 8 member rings. These tetrahedral layers are joined by 3 interlayer crystallographic sites that are represented by the blue and the red sphere and by this light blue octahedron. So the light blue octahedron is so it's 6 coordinated and it's occupied by iron 2+, magnesium 2+, and minor lithium. The valence of the iron was inferred by bond valence calculations. Then the blue sphere is representing an 8 coordinated site, and it's occupied by manganese 2+ and calcium 2+, while the red sphere is again an 8 coordinated site occupied by yttrium 3+ and lanthanoids. And laser ablation ICP-MS data allow us to see that there is a depletion of light rare earth elements compared to the heavy ones. The structure of perettiite is unique, but there are others that have a comparable tetrahedral layer, and I selected just 2. And these are 2 beryllium silicates. One is gadolinite, yttrium, in which we can recognize these 4 and 8 member rings. And we have also semenovite cerium that is topologically identical to perettiite. And it has also, as I mentioned before, the same twinning problem. We performed also Raman and FTIR spectroscopy. So the Raman spectrum was collected using a micro-Raman system with 488 nanometer excitation line. And we can immediately recognize that we have a problem with the luminescence due to the presence of rare earth elements. And only a long exposure time allowed us to see to identify some vibrations that are interpreted as silicate stretching, bending, and lattice mode. We performed also FTIR spectroscopy, and we can recognize very intense absorption band in the characteristic OH stretching modes. With the correlation by Libovitsky and Rossmann in 1997, we were able to give a quantitative content of H2O in the mineral, and it was around 0.5 weight%, so quite negligible. Just to make a short summary of the physical and optical properties, perettiite is brittle with hardness around 7. The cleavage is good parallel to 0.10. We calculated the density from the empirical formula, and it was 4.533 grams per reciprocal cubic centimeters. Concerning the optical data, as I already, so perettiite is biaxial, but we had serious problems because of twinning, so it looks conoscopically uniaxial. So the data that you see, so the alpha and gamma, should be interpreted as a maximum and a minimum of the refractive indices. So in order to achieve such a complete characterization of perettiite, of course we had to work in a team, so please let me thank Thomas Armbruster, Eugen Libovitsky, Mariko Nagashima, Eric Reusser, Detlef Günther, Hao Wang, Willy Bieri, and Adolf Peretti for providing the sample. And so perettiite yttrium was approved by the EMA Commission in 2015, and so probably a unique case in the world. It was even organized a party for that, and so in the next picture you can see we had a wonderful party in Lucerne to celebrate this event with lots of special effects. And with this I conclude, and I thank you very much for your attention. Thank you very much.
So we are here, Professor Sergei Krivovich from St. Petersburg University. So what do you think about the future developments of mineralogy and spectroscopy? What are the new highlights in this field?
Yeah, I think that the future of mineralogy lies in understanding the mineral diversity, knowing the diversity of the Earth, its evolution through space and time. And this can be achieved by using the precise techniques and methodologies, which is now introduced in the earth sciences from physics and chemistry. So this, of course, includes some various complicated and difficult spectroscopic techniques, new ideas in single crystal diffraction research, and also in general understanding framework of the mineral world. So we need a kind of new doctrine, new conceptual framework to understand minerals and their behavior. And another one, I believe this is an understanding of complexity of the mineral world.
Thank you very much. So what is the role of borosilicate in this mineral evolution?
On this topic we just submitted a paper with Bob Hazen and Ed Grew about the mineral evolution. I think that's the new mineral perettiite is an excellent example of their new and modern application of recent experimental technique to understand the formation of borosilicates in some exotic mineral localities like this Myanmar and Tibet. So, and I think that discoveries like this, they really excite people, and they really trigger some new research, as you showed it in your work.
We have here Professor Giovanni Andreozzi, and my question is, what is the future of mineralogy?
Well, the future of mineralogy, in my opinion, is being able to communicate with minerals, meaning that it's being able to understand the message they bring to us, because minerals are the travelers. They come from worlds very far from us. They come from time very far from us, and they have a message. They have an important message. They store information, as our friends Krivovic have told us. And the problem is that we don't understand their message. We don't talk their language. So spectroscopy, for example, is one way to talk with them. It's one way to read the information they bring. It is also one way to go back to our history, to the planet Earth history. The answer is in the combination of methods.
Okay, thank you very much. And since perettiite yttrium is a borosilicate, what is the importance of borosilicates in Earth?
Borosilicates are special for me. I did my graduation thesis on tourmaline, and I do continue working on tourmaline. Borosilicates are fantastic because they add complexity to the silicates. The boron is a special cation and is able to add some fashion to the world of silicates. So perettiite is an interesting mineral, and borosilicates are fantastic minerals in general.
Thank you very much.
You're welcome.
Grazie.